Hello Chem 1B, this is Chapter 19, Lecture Video 2, and we're going to start talking about balancing redox reactions. Now, redox reactions are much more difficult to balance than your run-of-the-mill regular reaction that you've been dealing with in the past. And the reason for this is because in redox reactions, we're not just balancing mass like we've done in previous reactions, right? You're looking for, hey, there's one atom on this side, there's got to be the same atoms on that side. That's mass, really. In redox reactions, you also have to balance charge, which makes them somewhat more complicated. Now, we're going to start off real easy. This is a relatively easy redox reaction to balance, but currently it is unbalanced. And we can tell that by looking at both the mass and the charge. Now, if we look at the mass, I have one tin on the left and I have one tin on the right. So the tin is balanced, and I have one iron on the left and one iron on the right. So the iron's balanced. So normally we'd just be, hey, it's a balanced reaction. But the problem here is that I have 2 plus 3, so I have a total 5 plus charge on the reactant side. And here I have 4 plus 2, so I have a 6 plus charge on the product side. Now, if we look at this, you notice quite quickly, hopefully, that this charge and this charge are not equal. And that means charge is not balanced, which tells us this redox reaction is not balanced. So we need to balance it. And the way we balance redox reactions generally, and we're going to go into more specific rules in the next slide, is by splitting the reaction into the half reactions that make it up, right? The redox reaction can be broken up into oxidation reaction, the half reaction, and reduction half reactions. So if we look at our stuff here, I know that tin is being oxidized because it's going from 2 plus to 4 plus. So I'm going to write out that reaction, right? So I have SN2 plus aqueous goes to SN4 plus, also aqueous. Now I need to balance this half reaction because we have one tin on both sides, but our charges aren't equal on both sides of the half reaction. So the way we balance charge is by adding electrons. And I know that I have a 2 plus charge on the left side and a 4 plus charge on the right side. So how can I make the charges the same on both sides? I can add 2 electrons to the product side, because if I do that, I get 2 negative charges on the products. -2 plus 4 gives me +2, which is the same as the other side of my reaction. So this is now a balanced half reaction. Next, I need to do the reduction half reaction, which is our iron 3 plus, because its oxidation number is decreasing. And so it goes to Fe2 plus aqueous. And again, these charges don't match up. I need to add an electron. To what side? In this case, to the reactant side, and only one of them, because -1 plus 3 gives me +2, which balances this half reaction. Now, in order to finish, typically we'll add both of our half reactions back together to get our full reaction. However, what we need to make sure of first is that the number of electrons in our 2 half reactions is equal, and they're not. So how do we fix this? We multiply this whole second half reaction by 2, and that'll give me a 2 here, a 2 here, and a 2 here. And now I can add these 2 reactions back together, right? So if I add these together, I notice the electrons, they're going to cancel, but everything else doesn't. And so my overall balanced redox reaction is going to have, that's a bad color, hold on, a 2 in front of these irons. Now, if we look at this redox reaction now, everything should balance, right? So our charges, our masses, everything should balance. So 2 plus, 3 plus times 2, that gives me 6 plus 2 plus. This is 8 plus on this side. I have 4 plus here, plus 2 times 2 plus. This also gives me 8 plus. So the charges are the same on both sides, and we have the same number of each element on both sides. So it's balanced. Now, as a general rule, we know that oxidation half reactions, the electrons are always going to be products because we're going from a smaller charge to a bigger charge, and that means you had to have lost electrons. And opposite is true as well, right? Reduction half reactions, the electrons are always going to be reactants because you need to decrease the charge, and you do that by adding electrons. So let's do a little bit more in-depth description because that was a very easy example. First, we always write the unbalanced equation when we're balancing a redox reaction. Then we split up into half reactions just like we did on the previous slide. And we do this without electrons to start. Then we're going to balance each half reaction. Now this takes 4 steps. First, we're going to balance every element that's not hydrogen or oxygen in the reaction. After we do that, we're going to balance oxygen atoms by adding H2O to one side of the reaction. And then we'll balance hydrogen atoms by adding H plus to, again, one side of the reaction. Finally, we'll balance charge by adding electrons, right? So by adding E minus to one side of the reaction. Once these are all done, our half reactions should be balanced. And then what we're going to do is we're going to make sure the number of electrons in both half reactions is equal. And we're going to do that by multiplying by factors to get them to cancel out when we add them back together. The final step is to add the half reactions back together and check to make sure your reaction is balanced. Now, this is balancing in acidic solution. We're going to talk about balancing in basic in a second. And we know we're in acidic because of this H plus here. Let's do an example problem, and I'll walk you through each step again on later slides. So we're going to react sulfite ion with permanganate ion to produce sulfate ion and Mn2+, manganese 2 ion, using half reactions. So this reaction occurs in acidic solution, so it's the way we just learned how to do. So the first step, write out the unbalanced equation from the wording there, which is sulfite plus permanganate goes to sulfate plus Mn2+. After this, we need to split everything up into half reactions. So I'm going to do this. It's pretty somewhat common sense what goes with what. Things that look similar should probably be in the same half reaction, right? So the permanganate and the manganese, they should go together. And then the sulfite and the sulfate should go together. And these are my 2 half reactions that I'm going to split apart. The next step would be to balance elements other than hydrogen and oxygen, but we got Mn, 1 Mn on both sides, 1 sulfur on both sides. We're good. So again, balance elements other than hydrogen and oxygen. Boom, balanced. Boom, balanced. Don't need to do anything. Oxygens aren't balanced in either of these 2 half reactions, but that's not what we're doing in this step. So we're going to move on. So we need to balance oxygen atoms by adding H2O. Now, in that scenario, it's dependent on how many oxygens we have currently, right? So if we look at this side, I have 4 oxygens on the right and 3 on the left. I need to add 1 H2O then to the left here because every H2O contains 1 oxygen, so 1 oxygen on the H2O plus the 3 oxygens on sulfite gives me 4, and I have 4 on both sides now. The same thing is true of my permanganate reaction. I need to add the 4 H2Os to the left because those 4 H2Os now have 4 oxygens on the right side, and to the right. I have 4 oxygens on the left, 4 oxygens on the right. This is now balanced for oxygen. And so this brings me to the next step, which means I need to balance hydrogen. And I balance hydrogen after having balanced oxygen because you may not have had hydrogen there, but now we do. So I have 2 hydrogens here. I have no hydrogens here. I need to add 2 H plus to that side. To the other side, I need to add 8 H pluses because we have 4 times 2 is 8. So these guys are balanced for everything except charge. So let's balance charges. So I know the total charge on this side is -2 because -2 plus no charge on the water gives me an overall negative charge. On this side, my overall charge is 0. So the only way I can make these equal is by adding 2 electrons to the right side, because -2 plus -2 is -4 plus +2 is -2. I have -2 on both sides now. Same thing is true for this guy, right? I have a -1 charge here. I have a +8 charge there. So this is +7 on the left, but it's only +2 on the right. So I need to add electrons to the right, to the left side now, and I need to add 5 of them, because 5 plus 6 plus 5 plus 1, -1, gives me -6, plus 8 gives me +2. And now, so I have +2 on both sides. The next step is to look at these and go, okay, well, what do I need to multiply by in order to get them to have the same number of electrons? And we're always looking for the lowest common value between our electrons. Well, I have 2 here and I have 5 here. The lowest common value between these two numbers, 2 and 5, is 10. So I need to multiply this reaction by 5, and I need to multiply this reaction by 2. And if I do that, I can get my two equations, right? So I have 5H2O plus 5SO3, 2 minus, goes to 5SO4, 2 minus, plus 10H plus 10 electrons for the first half reaction. The second one, I'm going to have 10 electrons plus 16H plus 2 MnO4 minus goes to 2 Mn2 plus aqueous plus 8 H2O. So that gives me these two. Now, at the end of the day, the last step here is going to be add the two half reactions, right? So if we add these two half reactions together, some things are going to cancel, all right? I can tell that these 5 waters are going to go away completely, and we're going to cancel out with these 3 to give me 3 waters on the right total. In addition, these 10, that's a bad color, these 10 H pluses here are going to cancel out entirely, with these 16 to give me 6 left over. The 10 electrons are gone, and so this gives me everything, right? So now I can go, great, my overall redox reaction would be 5SO3, 2 minus, aqueous, plus 6H plus aqueous, plus 2 MnO4 minus aqueous, goes to 2 Mn2 plus 5SO4 plus 3 H2O. And this is my overall balanced redox reaction. So let's talk about doing this in basic solution as opposed to acidic. How is that different? Really, there isn't much difference. We just have an extra step at the very end. What we do is we're going to balance an acidic solution first, and then we're going to add OH minus to both sides of the reaction. And the number of OH minuses at the very end that we'll add is going to be equal to the number of H pluses that we currently have. So let's do an example. I got this whole deal here. I want to split these into my half reactions. So the first thing I'm going to do is I'm going to write those out. All right, so I have CrOH3 solid going to CrO4 2 minus. And I have ClO minus going to Cl2 gas. And these are my two half reactions. I guess I have them on there, sorry. Now, the next step is to balance these. Well, so I got to balance chromium, but I don't because there's only one chromium on both sides, so we're good. Next, we're going to balance Cl. I have 2 Cl's here. So that means I need to put a 2 in front of ClO minus to give me 2 Cl's on both sides. Next, we're going to balance oxygen and hydrogen atoms by adding water and then hydrogen ion, respectively. Now I have 3 oxygens here. I have 4 oxygens here. This tells me I need to add H2O, liquid, to the left, one of them, because now I have 4 oxygens on both sides. I also need to add hydrogens to this to balance it out. I have 3 hydrogens here and 2 hydrogens there. So this tells me I need to add 5H plus aqueous to this side. Let's do this again with ClO minus and Cl2. So I'm going to add 2 H2Os here and 4 H pluses here. Next, we got to balance charges. And so I have 0 charge on this side. Both of those are neutral. And I have a positive 3 charge on this side. So if I want positive 3 to become 0, I need to add 3 electrons. Over here, I have no charge on this side, that's 0. And I have a positive 2 on this side, so I need to add 2 electrons there to this side to balance the charge. Next, we need to multiply these out to get the right values, right? So I'm going to multiply this whole reaction by 2 and this whole reaction by 3. Then we got to add them together. And if you add them together, you get this. You get this whole deal. At this point, we've fully balanced this reaction in acidic solution, and we need to balance it now in basic. And the way we do that is we convert the H pluses to OH minuses. I have 2 H pluses in this reaction. So what I'm going to do is I'm going to add 2 OH minuses to both sides. If this number was a 3, I would have added 3 OH minuses to both sides. If it was a 5, I would have added 5 OH minuses to both sides. Then I got to collect the terms. And what I mean by that is if I have 2 OH here and 2 H plus here, we can bring those together and form H2O, right? So this goes away and we get 2 H2O liquid on this side without that and without that. So that's my reaction. Now there's one other problem though. I have 2 H2Os here. I have 4 H2Os here. It's weird having it on both sides. We need to cancel the waters. So these guys go away. And this is going to be left with a 2. In other words, we get this fully balanced redox reaction in basic solution. All right, so let's do another example. All right, so let's do a practice problem. We have balanced the following reaction in acidic medium. Acidic medium is the same thing as saying acidic solution. They're like kind of synonyms. So we have this reaction. We want to know how many H pluses are needed to balance the reaction and on which side. So let's balance the reaction. So let's first split it up into the half reactions, right? So I know I have PbO2 solid goes to Pb2 plus aqueous, and I have I minus goes to I2 solid. I need to balance that. We'll balance the first one. So I know that there are 2 oxygens on the left side, so that means I need to add 2 waters on the right. By adding those 2 waters, I need to now add 4 H pluses to the left side. Now I need to balance the charge. Well, I have a 2 plus charge total on the right side, and I have a 4 plus charge total on the left side, so I know I need to add 2 electrons here. All right, so this guy is now balanced. Let's do the next one. The first thing I need to do is I need to put a 2 here to make sure I have two I's on both sides. If I look at this now, I have a -2 charge on the left side, and I need to have a -2 charge on the right side, so I add 2 electrons to the right, and now this is a balanced redox half reaction. The next step is just to simply add these guys together, right? Which gets me 4H plus aqueous plus PbO2 solid plus 2I minus aqueous goes to Pb2 plus aqueous plus I2 solid plus 2H2O liquid. And our question was asking how many hydrogens are needed to balance the reaction and on which side. Well, there are 4 hydrogens. I should have done that in red. There are 4 hydrogens on the left side. And so if we look at our options here, our answer is going to be C, 4 on the left. All right, so if you have any questions, as always, please come to my either discussion sessions or email me.